It is an absolute pleasure to be here today to see all of these wonderful people bringing together and elevating this beautiful industry and bringing a truly tremendous capability to the masses and communities abroad. My name is Ian Randall. I'm CEO and co-founder of Maglavero. I'm here with my colleagues, Josh and Rod Randall.
Good afternoon. I'm Josh Elvander. I'm the Senior Vice President of Maglavero. Just as a point of introduction, I've been doing advanced tech for about 25 years, most of it in aerospace, some of it in robotics. Thrilled to be here. What an awesome, awesome event.
Yes.
I'm Rod Randall. I'm also co-founder, and I'm chairman of the board at Maglavero. We're going to bring to you something different. So the question you might be asking is, if there has already been 750 aircraft that has been introduced from more than 250 companies with $10 billion of investment, why would anyone do anything different? That's a good question. And the answer we're going to try to explain to you today in the 30 minutes, although it hasn't started, so we may have more than 30 minutes.
There we go.
And we're going to try to explain how we bring technology to enable the deep penetration of urban air mobility into society, into communities, into our lives. And in so doing, we're going to try to explain how it all works. So Ian, would you like to start off?
Okay. So Maglavero is developing a novel propulsion platform to enable the next generation of quieter, safer, faster, all-electric urban air mobility vehicles to meet the mass market requirements of the urban air mobility market. This is one example of an aircraft that our technology can enable. Rod.
Let me have the clicker for a second.
Go.
One of the things that we all look for when we're looking at new markets, I've spent the last 20 years of my career in venture capital and technology investment. And so I've seen 10,000 companies. I've financed more than 100 deals. I've been in a number of projects with some of the smartest people around the world. And it's rare that a new opportunity, a new technology opportunity can address a $1 trillion market. It's not a $1 billion market, this is a $1 trillion market. And in order to address a $1 trillion market, it must penetrate deeply into society. So we've all seen that with mobile phones. Mobile phones is now a $3 trillion per year GDP. And what Morgan Stanley has predicted is that this market will be a $1 trillion per year GDP by 2040. They previously had predicted 1.4 trillion, but their more conservative adjustment is to 1 trillion per year in GDP, but now they've expanded it to a $9 trillion per year GDP by 2050. And so if you look at the breakdown of that market, much of it is going to be passenger orientation, but also the change between the previous prediction that they had, the 1.5 trillion, was previously not only passenger, but also cargo and regional, but they've now updated their views. Now, nobody is completely perfect in their views. The only perfect predictor of the future is time. But right now, they're saying that cargo and passenger will dominate. But in order to get this level of penetration, of this amount of economic value, you must penetrate deeply into the communities. And the biggest barrier of penetrating deeply into the communities is community acceptance, which is led by noise. The lack of a low noise solution, not just in flyover where it's relatively easy, but in takeoffs and landings where it's extraordinarily difficult, where you have not only steady noise, but unsteady noise, and we're going to explain that. If you look at the tremendous progress that we see around us with some unbelievable technology breakthroughs that have delivered not only amazing aircraft, but lots of progress in certification, lots of progress in partnerships, such as manufacturing partnerships to be able to create the volume of aircraft that will be needed. It needs to be manufactured in automotive scale, but with aerospace quality and technology and safety. The amount of financings I previously mentioned is already over $10 billion. And there's also been over $30 billion of orders that have been placed in the ecosystem. So lots of progress. Even though we have gotten tremendous market progress in terms of the entry into urban air mobility and regional air mobility and advanced air mobility more generally, the market entry is one thing, and I think we are there. We're good enough. We have safety requirements that are largely met by many, many solutions. Now, the mass market adoption requirement is going to be more stringent. It's going to need more activity. It's going to need even better safety requirements. Noise, where there's a number of solutions today that are great for flying overhead and taking off and landing in airports. But in order to penetrate into the neighborhoods where buses and where commuter rails and where people live, play, and work, you're going to need a much quieter solution. So while 15 dB quieter than helicopters is good enough for the market initiation, in order to get deep penetration, you're going to need 25 dB or more quiet. And that is extraordinarily difficult due to the physics. Also, cruise speed. The initial ability to deliver 150 miles an hour is going to be great. But in order to penetrate deeply, you got to be able to go fast enough to expand the market opportunity. You need to be able to not only do short trips, but you need to be able to do longer trips. Your capacity is fine to start with 4 passengers and 1 pilot, but ultimately we need more passenger capacity. We need 6 passengers and their luggage. So you can have a 5-person family travel to the airport, or 6 commuters travel from the suburbs to another suburb. And also, at the end of the day, in order to achieve the adoption that we all have in our hands with our cell phones, we need industrial design. It not only needs to be functional, which is okay to start the market, it's going to need to be beautifully inviting. If you look at some of the recent press that's beginning to recognize the issue of noise, there is still a lot of work to be done because the sound of these devices will be important. And it turns out this noise issue is not just arbitrary. It's not just a human factor. There are equations that govern the issue of noise. So there is a concept of day-night noise level, which is regulated typically by communities. And for example, in this chart, I know it's complicated, and it's a log chart, which makes it even more complicated. But what that vertical line at 65 dB, an average day-night noise level, represents is the limit of many communities around the world. Some of them are 55. Some of them are 45 dB in noise limits. But a current helicopter is limited to 40 flights per day, which is not economically justifiable enough to justify the investment, let alone the potential. So if you can make that vertical flight vehicle quieter, by 5 dB, you can move up on that scale. By 10 dB, you can move up on that scale. The vertical line is the number of flights per day per session that you could possibly achieve. But if you were to, for example, make a vehicle that's 12 dB quieter, which is the current standard, then you can grow from 40 daily flights to 500 daily flights in a region. If you can expand that to possibly 15 dB quieter, 1,200 daily flights. If you can make that 20 dB quieter or better, the number of flights dramatically expands. And it's not that you would blot the skies with eVTOLs. It is that having more capacity due to the lower noise footprint allows you to be viable in any community, in any neighborhood, whether it is 65 dB, 60 dB, all the way down to 45 or 50 dB. So that's the important thing. Some communities will demand the noise footprint be much lower. So to access the deep penetration that Morgan Stanley projects, you need to be able to get deep into the noise. So if you were to take that chart and reconfigure it and look at the volume of flights as a proxy to the accessibility to the broad market, and if you were to measure along the x-axis the amount of noise reduction in dBA from a helicopter, you can see 40 flights per day for a helicopter. This is a log scale vertically. But if you were to make that a linear scale, you can see there is dramatic increase in market size, market addressability, increase in the economic potential of the entire market. And so that's why noise is critically important, but not just in flyover. Noise is critically important in takeoff and landing, where we live, work, and play. At the end of the day, helicopters are too loud to achieve this market potential. Distributed electric propulsion multi-rotors are quieter, significantly quieter. But in order to achieve the true potential of deep market penetration of urban air mobility and regional air mobility, you need a much quieter solution. Ian, why don't you talk about how we think we can do it?
So Maglavero is developing what we call the maglev hyperdrive, and we believe it can have a dramatically lower noise profile than traditional prop rotors in multi-prop rotor configurations. Ultimately, lift is generated mostly in the outer four blade spans. So you have most of the lift coming from the outer blade span, where it's traversing the largest amount of area as well as moving the fastest through the air. This also generally tends to lead to where we concentrate the loading along the span of the blade. It disproportionately is loaded toward the outer blade spans, and this is also where most of the loading noise comes from. There is steady loading noise, and there is unsteady loading noise. Traditional distributed electric propulsion systems can be similar. They have a similar loading profile, where the outer loading is concentrated on the outer blade spans. This is also where you have much of your noise source. But because they break it up into more smaller rotors, they can be significantly quieter than your large helicopter prop rotor configuration. Unfortunately, unsteady loading affects all rotary wing systems. It is the rate of change in pressure per unit time, and it's how fast you're changing your loading that adds another unsteady loading noise source to the sound profile of these vehicles. So in this configuration, you see a large rotary wing helicopter moving very slowly with the same blade loading, same tip speed, same disc area as a multi-rotor system. Its steady loading noise may be louder than a DEP, but its unsteady loading noise contributions may actually be quieter. So distributed electric propulsion can be much quieter in steady loading, but they are challenged with unsteady loading noise factors. In this slide, created by an industry proponent, Dr. Kenneth Brentner with Penn State, he showed that the unsteady loading noise from a slight cant with inflow at an angle to a rotor system can have actually a fairly significant impact on the noise profile of a rotor system. So you have a isolated rotor of one disc area with equal disc area to multiple more distributed electric propulsion systems, each with the same blade load, each with the same the blade tip speed. And the difference between the unsteady loading noise of a multi-blade system versus a isolated rotor system is going to be fairly significant. In this case, 25 to 28 dB, because the blades are going from advancing to retreating in much less time than your large rotor system. So, given this, we took a ground-up development approach, looking at where the most effective use of lift is and only utilizing that area so that we can focus on loading that area much more effectively. So you have your blade loading of a small, low solidity, low blade area system, and we can dramatically increase the number of blades and therefore dramatically decrease the loading per blade without the traditional efficiency losses that normally come with taking that load. And then because we're only using these short blades, we can load them along the span much more effectively so that they're much more uniformly loaded across the span of these blades. And then by doing these three things together, we can spin them much slower, less than half of the traditional tip speeds of what you normally have in these prop rotor systems. And in this configuration, we can also add it with a contra-rotating or a co-rotating configuration for flexibility with various aircraft systems. Ultimately, we believe we can have a much higher hover lift efficiency, requiring less power and hover. Oh, let me go back, sorry. Less power and hover, more efficiency in cruise, as well as less than half the tip speed, and an order of magnitude less blade loading, leading to much less unsteady loading noise as well in cruise and overflight, and ultimately much lower noise. So you must be asked, why don't you just try to do this with a roller bearing? It's really for one of two or so reasons. If you were to try to do it with a rolling bearing element system, you'd either be afflicted by the thermal or the centrifugal loads, driving your service, your weight of the system up to be able to meet the service life requirements of this novel breakthrough market, or B, you'd be light enough for the application, but you'd have a fairly pitiful service life of this rotor system. And that's where our innovation comes into play. On the right side of the graph, you can see a 10-meter bearing that is 40 tons. So our rotors are smaller than that, but you get an idea of how the mass changes with the size of the system. We take a system where it's like a maglev train on the ground, which has the benefits of linear maglev with zero rolling friction, higher speed efficiency, less power per unit distance, and less maintenance. And we apply it to a ring system so we can both be able to have the authority and control of the bearing with the motoring efficiency of linear maglev and linear electric motors. Rod, here we go. I'm going to pass it back to you.
As a result, what we've created is a fundamentally new architecture. It is a ground-up design with the specific intent of creating ultra-low noise, but in order to do that, you have to start with an ultra-high efficiency system aerodynamically. The hoverlift efficiency is designed to be more effective. It uses only the most effective parts of the blades. And then instead of the small number of thick, heavily loaded blades turning fast, it is a large number of relatively thin, relatively light loaded blades turning relatively slow. This addresses the top 3 issues of noise. So as a result, our maglev hyperdrive architecture allows it to be much quieter, allows it to carry more payload. So for the same footprint and the same energy consumption that some may use to carry 5 people, we may be able to carry 7 or more people. With more payload, we also need more redundancy. And intrinsic to this design is integral fault tolerance. So while distributed electric propulsion allows a single rotor to fail, which often needs to be matched by failing another rotor on the other side to keep balance and anti-torque, we are distributed circumferentially around the rotor. We can lose many different inverters without any effect on the loss of any rotor system, making it fault tolerant, making it highly reliable, giving it more reliability, and because it's a rotor system with a lot of inertia, it also enables auto rotation, not unlike the way helicopters can do auto rotation in the case of a complete power outage. And also in the configuration we showed, which was a tilt rotor, they don't all have to be tilt rotors, it can be much faster. Now, this has never been doable before, and it is only now doable due to the confluence of many different technologies coming together. You've got generatively designed additive manufacturing that is now capable of doing 3D metal printing. We announced this morning a relationship with General Electric that allows us to 3D print titanium with a biomimicry style, ultra lightweight, super strong, super stiff architecture that allows us to build this kind of a system, which has never been doable before. This was 5 years ago, there was no certifiable 3D printing of titanium. Large manufacturing, high strength, lightweight composites are now doable. 5G, ultra reliable, low latency communications, artificial intelligence, machine learning, high energy magnetics, and batteries are now possible. But most importantly, very large scale, cloud scale, high fidelity, multi-physics simulations. Computational fluid dynamics, aeroacoustics. Aeroacoustics is amongst the most difficult to simulate. This is why not a lot of people have predictions on where they're going to be, because aeroacoustics needs a molecular level simulation technology which requires immense compute. And so this was not even doable even 5 years ago. But now it is, and we can characterize them. This is what enables us to build this technology.
Why don't you leave it there? All righty. Let's see. I'm going to go back for a sec. So Rod and Ian have talked about the problem, talked about the opportunity, and talked about a really unique approach to solving it. What I'm going to do is spend a couple minutes talking about what we're doing on the ground every day to turn this into a demonstrable reality. So we all know the crawl, walk, run approach, and it's a very proven approach to take a new technology, an advanced technology, and mature it. It's a very proven engineering development path, and I just wanted to add a little bit of spin, crawl, walk, run, fly, because that's what we want to do. So the key element of it is, as Rod mentioned, this very sophisticated multi-physics model that takes into account both electrodynamic, steady and unsteady dynamics, structural and steady and unsteady dynamics, and steady and unsteady aerodynamics. So it's this massive multi-physics, multimodal model that we're continuously working on and refining. Beyond that, we follow this traditional methodology. We define our requirements, then we start by proving out some of the individual elements, and then we do some subsystem development, we do some subsystem integration tests, and then we work our way into integration tests at both subscale and increasing larger scope, increasing larger scale. At the heart of it is this multi-physics model. We continue to generate empirical data to validate this model, because if we validate it, and we have validated it, that means that we can show that it scales. And if it scales, then we have a market, and we have a product that can address that market. And we really believe that because the data so far shows that. If you look at it, you'll see actual pictures. We are actually building and testing. Just last week, we finished a subscale integration test. We were actually collecting thrust data. The thrust data matches very well with the models that we've generated, and that shows that our models are valid. It's very, very fascinating. It's a wonderful time to be part of Maglev Aero. A lot of stuff going on. So, riffing on this crawl, walk, run, fly mantra again, we have a plan to start with, as I said, increasing scope as we do these integration tests and build larger and larger systems. But as we grow it, we will look for opportunities. Even though our eyes are on the prize, which is urban air mobility eVTOL, which is a large-scale system, a propulsor for a large-scale system, there may be opportunities for smaller systems, such as heavy lift drones, or perhaps single individual flying machines based on the imminent Mosaic rulemaking that's coming out of LSA. And if those opportunities exist, that's an early entry into the market. And that's an opportunity for us to generate some more revenue and to build our company and to build our technology. So taking kind of an eagle eye approach to the entire opportunity landscape, we are developing a propulsion system. And that propulsion system could be implemented in a small wingless rotor. It could be a lift plus cruise. It could be a large winged rotor, such as implementations that have been shown earlier. So it's all a matter of figuring out the configuration, the market, and the opportunity. Market estimates forecast roughly $500 million in urban air mobility. But there's still hundreds of millions of dollars in opportunity in regional freight logistics and regional air mobility. There may be other use cases that we will discover, such as medevac or industrial or recreational even. And as those markets avail themselves, we will match it, and we will take this technology as far as we possibly can. But the neat thing about it is, because we're building this ultra-quiet, very efficient, and safe, by the way, we didn't talk about safety, but it's got a big safety element, that allows us to apply it to a lot of different market opportunities and to grow our business.
Perfect. So one of the things that we wanted to do is sort of display a bit of a gallery of application use cases. It's not just, we're not building the vehicles, we're building the propulsion system that will enable an entirely new category of vehicle system performance and possible market penetration. Whether it's small, medium, or large military vehicles like those on the left, or whether it's small, medium, or large medevac vehicles like those on the bottom in the center, or whether it is the advanced high-speed, high-efficiency urban air mobility tilt rotor like the one in the center, or possibly a IRIS-covered lift plus cruise that is essentially a blended wing version. So when in cruise, it could operate like a blended wing with a combined propulsion of a hyperdrive for vertical lift and electric propulsion for the horizontal cruise. And that may be a different certification profile. And also there could be smaller vehicles like the city hopper vehicles envisioned in Westworld, for example. So the issue is the airframers that we look to partner with, the aircraft manufacturers that we look to partner with may have a number of interesting application use cases of our technology. But we believe the advantage that we bring is expand the market. And when we look at the kind of things that we could do, we've been approached by a media company that wanted to create a vehicle for maybe one of their unnamed superheroes. But this could also be an ultra high performance and ultra luxury vehicle, which will allow us to envision how it all works and also bring to market a variety of different use cases in a variety of different cases. So at the end of the day, we believe industrial design will be key to letting the consumers develop an emotional, intrinsic attraction to be able to engage this marketplace. So in addition to having super high efficiency, ultra quiet noise, we believe that we can enable an entire generation of aircraft that will cause people to want to be engaged, to be emotionally attached. And at the end of the day, we've been financed by institutional venture capital. Breakthrough Energy Ventures is the group that is founded by Bill Gates and is financed by the many other tech billionaires, including Jeff Bezos and Mukesh Ambani in the mobile world, and Richard Branson, and there's a number of, if you look at Breakthrough Energy, there's a tremendous number of interesting investors. We also have been financed by Material Impact, which is a material science-focused venture capital firm that also looks to make a material impact on the world. So it's a double entendre. I thought it was a beautiful name. And so as you may imagine, we have a lot of material science involved. But at the end of the day, this is Maglev Aero. This is our story, and we're sticking to it. And I think we've got a couple of questions. We got a couple of minutes in case there's anybody that may have a question or two. And I don't know how we get the questions, but if there are questions, we have 1 minute and 46 seconds. And if there are no questions, then we'll be able to finish early and under budget. Okay. All right. Thank you very much.
Thank you, everybody.